Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face Trending List, published on July 26, 2025, about 3 days ago. This paper introduces a new method that achieves better performance while using only half of the tool use budget required by existing approaches. The paper is titled Agentic Reinforced Policy Optimization, and the efficiency gains here are pretty remarkable. The key idea is to help large language models better handle complex, multi-step tasks that involve using external tools, like a calculator or a search engine. Also, for those who want to get their hands dirty, the authors have released the complete project on GitHub. You'll find the official code, of course, but also their model checkpoints and datasets. It's a full walkthrough, covering the initial fine-tuning, the main RL training, and the final evaluation. On Hugging Face, you'll find the ARPO model checkpoints. They've shared 8 billion and 14 billion parameter versions, all ready for you to download and experiment with. So this first figure really visualizes the core idea behind the paper. On the left, we see a chart of token entropy, which is a measure of the model's uncertainty. Notice how after each tool call, the entropy spikes dramatically. This suggests the model becomes unsure of its next step right after getting new information from a tool. The paper's method, Agentic Reinforced Policy Optimization, or ARPO, is designed to focus on these uncertain moments, and the payoff is clear on the right. ARPO consistently outperforms other methods, while the bottom chart shows it uses significantly fewer tool calls during training. Building on that idea of token entropy, let's dive into this next figure. The charts on the left visualize the model's uncertainty. For the Hotpot QA dataset, which involves searching for knowledge, you see huge spikes in entropy right after each tool call. The model is clearly less certain after getting new information. The effect is smaller for the AIME 2025 math dataset. And the word clouds on the right show us why. High uncertainty is linked to words like information and determine, while low uncertainty involves procedural words like think and Python. So this next diagram breaks down exactly how the method works. On the left, we see what's called entropy-based adaptive beaming. After each tool call, the system measures the change in its own uncertainty. If that uncertainty jumps past a certain threshold, it branches out, exploring multiple different reasoning paths at once. This focuses exploration right where it's needed most. Building on that, the diagram on the right shows how the model learns from these branches using something called advantage attribution estimation. This is basically a method for assigning credit. The system learns to give different rewards to the shared part of the reasoning path versus the individual branches. This credit assignment helps the model figure out which specific tool use behaviors lead to better answers. Alright, moving to the results. This table really puts that method to the test. It shows the overall performance on 10 challenging reasoning tasks, split between mathematical and knowledge-intensive problems. They compare their new method, ARPO, against several other reinforcement learning approaches, like GRPO and DAPO, across different models like Qwen and Llama. And the pattern is crystal clear. In almost every single case, ARPO, shown in the last row of each block, gets the highest score. This just drives home that their strategy of adaptively exploring those uncertain steps really pays off. Okay, so after seeing those results, this next table moves into an even tougher domain, what the paper calls deep search tasks. These are really challenging problems that require complex, multi-step information gathering, tested on benchmarks like WebWalker QA and Humanities Last Exam. And the results are just as impressive. If you look at the last row in each block, whether it's an 8 billion or 14 billion parameter model, adding ARPO delivers the top performance consistently. This is especially notable because it outperforms many larger models, showing the method is extremely effective. So to wrap things up, the key insight is that by focusing exploration on moments of high uncertainty right after a tool use, the model learns complex behaviors much more efficiently. This leads to better performance with a smaller tool use budget. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.